In the previous lessons, we learned that the problem is reflections, and the solution to that problem has two parts. Design our traces to look like transmission lines, and then terminate them in their characteristic impedance. And a transmission line is characterized by a controlled geometry. That's why we call them controlled impedance traces. If that geometry is not controlled at any point, then an impedance discontinuity may result and a reflection may occur at that point. So we need to control the geometry of our traces throughout the entire length of the trace. This lesson will illustrate some common ways that impedance control might be lost when we design our boards. And the first potential problem we're going to look at is the placement of the terminating resistor. Here's a driver, here's a trace driving down to a BGA, and we're going to connect to this pin under the BGA. So we need to place a terminating resistor for this controlled impedance trace. And I'm showing three options here. One is what we almost always do. We place the terminating resistor in front of the BGA and then route the trace on underneath the BGA. The second is somehow placing a terminating resistor right at the pin under the BGA. And the third is going and connecting to the BGA and then extending the trace out to the other side and putting the terminating resistor there. And we're going to look at these three alternatives and evaluate the performance. Now, I am a big fan of the potential for embedded passives. And I'm a little bit surprised that our industry is not moving more rapidly in that direction. It seems to me that figuring out a way to put an embedded passive right here under the BGA in the board would be the ideal way to terminate this trace. And I will tell you that the best way to terminate this device and this line is this way, putting a resistor directly at the pin. Of course, we have the access problem. The next best way is to extend the trace out beyond the BGA and place the terminating resistor out here. That, of course, gives us a geography problem where we're using a lot more real estate for the traces. The poorest way is what we always tend to do, and that's put the terminating resistor out in front. Now, I'm going to show you a series of three simulations, one for each of these placement strategies, and show you what the signal looks like. And the first is placing the terminating resistor directly under the pin. Under this simulation, using the Hyperlinks simulation tool, we have a driver, we come through a transmission line, we come to the pin underneath the BGA, and at that same point we place a terminating resistor. And this is what the signals look like, and they are nice and clean and really nice. And this circuit is going to work perfectly when it's done this way. In this simulation, we're going to place the terminating resistor in front of the BGA, the way we typically do it. So here we have the driver, here we have a transmission line, we come down to a terminating resistor. Then we extend the trace as another length of transmission line underneath the BGA and connect to the pin. The problem with this approach is this becomes an unterminated stub. And here's what the result looks like. This black line is the driver, but this red line is what the signal looks like at the BGA. Now, is that okay? Well, somebody has to make that judgment. Maybe it is, and maybe it isn't. But as rise times get faster and faster, this problem will get worse and worse, this problem with the unterminated stub. The third is extending the trace beyond the BGA and then placing the terminating resistor. Here we have a driver, we have a transmission line down extending underneath the BGA to the pin. Then we extend the trace as an extension of the transmission line out to the far end, then place the terminating resistor. There are no unterminated stubs when we do it this way, and here's what the result looks like, and it's just as clean as the first simulation was, That was placing the terminating resistor directly at the pin. And so this is the preferred approach to where to place the terminating resistor if we can't get directly under the pin. The next problem we're going to look at is the problem of Ys. We have a driver, we have a trace, and then we branch into two other branches. And we call this right here a Y. So if we have a 50 ohm trace and we branch into two other 50 ohm traces, and then we terminate each of them with a 50 ohm resistor, that seems to be okay, but it's not. Because what we have is two 50 ohm traces in parallel look like 25 ohms at that point. So we have an impedance discontinuity of a 50 ohm trace then looking into a 25 ohm set of traces beyond that point. There'll be a reflection here. There's a couple of ways we can deal with this. The first is that we bring a 50 ohm trace down and then we branch into two 100 ohm traces. And then we terminate those 100 ohm traces in 100 ohm resistors, and those 100 ohm traces in parallel to a 50 ohm equivalent at that point, and there is no impedance discontinuity. That's one choice. The second choice is to bring the point of the Y back toward the driver so that this distance right here is much shorter than the critical length. Then this impedance discontinuity doesn't particularly matter. Drivers in general, most drivers, are not very sensitive to what they're driving. It's the trace that needs to see the correct termination, but not the driver itself. So if we bring this branch back here, closer to the driver, well within the critical length, then this circuit ought to work pretty well. Howard Johnson has shown in one article that a third approach is take your 50 ohm trace, branch into two other 50 ohm traces, but then put a series terminating resistor here at the beginning of each of these branches, and then terminate with 50 ohms. And these end up looking like 100 ohms from back here, the 200 ohms parallel to 50 ohms, and there is no impedance discontinuity. The problem with this, of course, is that we are adding some components. That's the first problem. And the second problem is we have a voltage divider here with this 50 ohm resistor and this 50 ohm resistor. And so we cut the signal level down at this point by 50%. And that may not be a tolerable option in our systems. A system or circuit design engineer needs to address that particular question. Another issue, most designers now know how to deal with this, but we have to be concerned about transitions. If we go from a 75 ohm trace on one layer to another layer and design the trace there as a 50 ohm trace and then back up as a 75 ohm trace, well, that of course is going to set up impedance discontinuities at these transitions, and this would be a bad thing. What we have to do when we transition layers is if we have a 75 ohm trace on this layer and we go to another trace layer, we have to have the same 75 ohm trace on that layer. And then we come back up to the first layer, we have to have the same 75 ohm trace on that layer. Now remember, the way we got a controlled impedance trace is by controlling the relationship of the trace width, the trace height above the plane, and the relative dielectric coefficient of the material, and to a lesser extent, the thickness of the trace. Well, if we go from one layer to another, we are probably changing at least one of those parameters. Maybe the distance to the plane, maybe the relative dielectric coefficient. So if we do that, if we go from one layer to another and we're changing one parameter, then in order to keep the same relationship, we might have to change some other parameters. So it's not unusual that if we go from this layer to this layer, the trace width has to change in order to maintain the same impedance on the two different layers. Now, any plane can be a reference plane. The power plane or the ground plane can be a reference plane for a transmission line. And if that seems a little awkward for you, well, just recognize that the power and ground planes are connected with a whole bunch of bypass capacitors all over the board. And from an AC standpoint, the planes are shorted together. The only distinction between the voltages on the planes is a DC distinction, not an AC distinction. So any plane can be a reference plane, and then we can ask the question, well, what happens if, in this case, we have a signal above a plane? That's fine. The return is on that plane. But what happens if we transition to another trace layer? Well, if the trace layer is on the opposite side of the same plane, well, then that's pretty straightforward. The return signal is simply going to transition to the other side of the plane and then back up to this side of the plane again. And we aren't going to lose any relationship because of loss of control of the return current. The return signal is going to be on the plane in either case when we do this kind of transition. But what if we go from this signal layer all the way down to another signal layer down here and reference a completely different plane? How does the return signal get from this plane to that plane? And the answer to that question is we don't really know. And that's not a very satisfying answer. Now, the practical reality is we've been doing this for a long time and we seem to get away with it. And the practical answer is the return signal probably gets there through a nearby bypass capacitor. But the problem with that answer is it's not definitive. We probably get there this way. We think we get there this way. That's not very satisfying if we're really concerned about signal integrity performance of our boards. So what can we do about this? Well, one way is what some engineers advocate is dropping a bypass capacitor from this plane to this plane. That provides a path for the return signal to get from one to the other, and then put another bypass capacitor here so that the return signal can get back up again. We're not dropping the bypass capacitor for power distribution system reasons. We're dropping the bypass capacitor to provide a path for the return signal. That's one solution to this, one answer. The second answer is we just leave it and trust to chance that the signal is going to get there. And in our experience in the past, most of the time that's happened and we've gotten away with it. There are some system engineers and some circuit design engineers who will say you can't do this. They will set a design guideline for the board design that says you can't transition from one layer to a completely different layer, referencing a completely different plane. And if they are setting that design guideline, this is one of the reasons why. They're worried about where the return current and the return path is going to be. Now, we at UltraCAD have never particularly worried about this, and we've never been burned by this kind of transition. But if we had a system engineer who said you couldn't do this, we would honor that and we wouldn't argue very hard against it. I'm guessing that maybe 10% of the system engineers around our country would object to this kind of transition. There are some engineers who would object to this kind of transition too, and frankly, I think that's unreasonable. I think this is perfectly fine. It's highly unlikely that this would cause a signal integrity issue. But this one is a little more problematic, and it would not be unreasonable for somebody to say on a really critical design that you can't do this. Now, one of my favorite topics is don't route a trace over a slot in the plane. We can wonder, how did the slot get there in the first place? Well, maybe you finished the board and all of a sudden the circuit design engineer comes up and says, son of a gun, I forgot this one resistor. I've got to get this resistor in here. Can you go ahead and place it? And the situation is, yeah, you can do that, and you can go through about 4 hours of rerouting it to get it done. Or you can just drop a little slot in the plane. Then you can route the trace for that resistor in here and get the job done in a couple of minutes. Well, this signal going along here is referenced to the underlying plane. The return signal comes back here and sees this slot, and where does it go? Well, it has to go up around the slot, and that way. Then it will come back underneath the trace. So the return signal is going to stay underneath the trace as long as it can, but it has to go up and go around the slot. There are 3 reasons that you should not do this, and I'm going to cover all 3 reasons in this series of lessons. There are no reasons to do this, but there are 3 really good reasons not to. And the first we're going to give in this lesson is that this gives an impedance discontinuity. And there may be a reflection that gets set up at this point. We have lost control of the relationship between the parameters, the width of the trace, the height above the plane. All of a sudden, this return signal is not underneath the trace anymore, and the relative dielectric material. So we've lost one of those, and that is the height of the trace above the return signal on the plane. Don't do this. And the last one I want to cover is stubs. Be careful of stubs. I'm giving 4 illustrations here. There's a driver. Here we got a trace that's running around a variety of receivers here and a terminating resistor down here at the end. This is a good way to route. We bring the trace up to the receiver. That's fine, as long as that's shorter than the critical length. If we come down here, this is not good, coming down here and then running a stub up to a receiver. This looks like a Y at this point. We don't want to do that because this now sets up an impedance discontinuity. This is good because we're terminating right at the receiver. And then this is bad because we have an unterminated stub here. The signal will go down to the end of this line and reflect back. From a transmission line standpoint and a reflection standpoint, this is bad because it will set up a reflection. From an EMI standpoint, this is bad because this looks like an antenna and it will radiate EMI out into the world. So 2 and 4 we don't want to do. 1 and 3 are good. So here are the takeaways from lesson 2.3. Be careful with the placement of terminations. Be careful where you put them, and don't inadvertently run some stubs out beyond the terminating resistor. Avoid reflections at Ys. Be careful about trace layer transitions, and be careful what we do there. Do not route a trace over a slot in a plane, and avoid unterminated stubs.
Looking to advance your career by acquiring new skills? Tired of expensive off-site training programs? Wish you could learn from the best instructors in the industry? Look no further than Live Lessons. Self-paced, personal video instruction by the world's leading technology publishers. Each live lesson comes with a DVD featuring 3 to 4 hours of instructor-led classroom training, sample program code that allows you to work along with your personal instructor, and an example-rich study guide. Live lessons allow you to watch the entire course from start to finish, or navigate directly to any of the individual lessons. You'll literally watch over the shoulder of your instructor as he shows you how to build state-of-the-art applications. Live Lessons, the power of the world's leading technology experts at your fingertips. To learn more, visit mylivelessons.com today.